Okay, so I'm going to make a start. Now, this week we're talking about multi-threading, and I'm quite excited about this topic because this is the first week of content whereabouts. This is entirely new content to this course. These are slides that I've entirely put together by myself, so if there's errors on them, they're all my fault. But before we do kick in and start talking about multi-threading, just a couple of housekeeping things. With assignment 2, I'd hope to get marks for you by today. We still have about 10 or 15 still to mark. The marking's been quite difficult because people have literally failed test cases in every different way imaginable, which is kind of good. I mean, like, one of the things that we're focusing on is performance and efficiency of how you do stuff. And one of the ways in which people have failed is a lot of weird memory corruption bugs. And so people's code, what they were doing is they were ending up with undefined behaviors. And what an undefined behavior is say if you're using, I don't know, standard copy or standard findIf or something like that, and you're passing in a start iterator and an end iterator. What happens if you pass in an iterator, like say an end iterator and an end iterator into findIf? What might happen in that situation? Does anyone know? It might not search anything. Formally, the behavior is undefined. Formally, the behavior is undefined. So what's happening? And I didn't set out a test case to do this. I'll be clear about this. I didn't set up a test case deliberately to have an end iterator go in and an end iterator go in. Some people end up with some bizarre bug that caused that to happen. And when that happens, the behavior is undefined, and depending on the compilers, that undefined behavior gets handled in different ways. Now, in the case of GCC, which we're compiling on, undefined behavior, as I rapidly discovered, doesn't even print segmentation fault to the screen. Your program just exits. No errors, no nothing. And in terms of marking that, that's been a real nightmare to sit down and go, why am I getting absolutely nothing out? And so what we've done is we've found an extra flag that we can give the GCC compiler, which is called ifSanitize address. And what ifSanitize address does is when it has some sort of undefined corruption behavior, GCC is able to insert additional debug information into your code and print this out. And the reason why I'm showing you this is when you actually go and take a look at your assignment marks, which are not out yet. They'll hopefully be out later on this afternoon, if not, worst case, by Thursday. But if you go and you see your output, it might look like this. You might end up with, test 1, test 2, pass, that's fine. And then you get down to this issue. And what's happened is halfway through this code, someone in their code somehow has ended up with this address sanitizer heap buffer overflow error. So I'm assuming what they're doing is in their code, they're using some sort of dynamic memory, using just a standard C-style array, and they've basically run off the ends of the bounds of the array. And their code's crashed. And so this ifSanitizer bug allows us to print out at least a little bit of debug information about what's going on. And the reason why I'm showing you this is maybe for assignment 3 and assignment 4, you might want to include this. Once I've finished marking, I might actually do a short little notice onto the course website showing you how to use it. But the short version is, in the flags up the top, you can say ifSanitize equals address, and this sort of information gets printed out. For us marking this information's been helpful, not in terms of fixing your code, but at least having an idea of what's gone wrong. I've got a second screen here. Okay, same thing again. So unfortunately, this poor student has had memory issues the entire way through their code, but they've got different ones in different places. And so what's happened up on this top one is straight away, it's come in and crashed with an unknown address. And I'm assuming that an unknown address is probably you've tried to dereference on a null pointer or something like that. That's happened twice, and then over here you've ended up with a crash whereabouts you failed to allocate. And actually a lot of people, I would say 1 or 2 people in the class, have this error on test 15 of failing to allocate memory. What's happened there is your move constructor hasn't worked. Your move constructor is designed to move physically one piece of memory to another piece of memory using standard move. And if you didn't provide a move constructor, or if you did your move constructor wrong, e.g. your move constructor was actually doing a copy, when I created, and I'm not joking about the fact I did this, when I created 7 million dimensional Euclidean vector, okay, and then I tried to move it, swap it, I literally called standard swapping it with a second 7 million dimensional Euclidean vector. I tried to swap that, I think, 11 million times. And basically, what's happened is, actually in this case, only the second swap has caused you to run out of memory. Now, using standard swap, using a correct move constructor, that is very, very, very fast. And so this is test 15. It was only worth half a mark, but this was a real tough test, that if you've done the move constructors correctly, you'll pass. If it didn't, you'll get an error that kind of looks like that. So I'm not showing you this poor student's code, because, well, it's not their code, it's poor student's results, because they did anything particularly wrong. What they did do wrong is they have these errors on the edges of their memory that they haven't considered when going and thinking about how to do stuff. So in future, maybe take a look at using the F-sanitize up there. I am yet to decide whether or not I'll keep including this in the test cases, because the F-sanitize flag, what it does is it puts in extra debugging symbols into your code, so therefore it slows your code down. So it's good for testing, it's not good for production code. Okay? But you might want to take a look at that. One other thing to do with assignment 2, and actually assignment 3 moving on, really unfortunately I have to talk about plagiarism. Please don't plagiarize. That's the short version. Please do not plagiarize. A lot of people, what they do is a problem with what's called collusion, which collusion is whereabouts you work too closely together with your friends. Okay? It doesn't mean that you even necessarily copied one person's code and submitted it as your own. Look, a couple of people have done that, and again, probably this afternoon, they'll get the formal emails about that. Do not take code and just copy it directly from someone else, because that's very easy to pick up, and that's clear-cut plagiarism. What is more difficult to deal with is collusion. And collusion is where you sit down and you work side by side with somebody. You still write your own code, but you work side by side along somebody else. And our plagiarism detectives picked this up, and it's a very hard issue to deal with, because you'll say, you wrote your own code, you just talk to your friend. And I'll look down the code, and every single function, even if it's written slightly different, will be in the same order, and it will be in the same sort of thinking, and it'll have the same sort of bugs. And that is actually still plagiarism. Okay? So I encourage people to work together in terms of talking, thinking about how you might test things, maybe even talk about writing a test case, pass the test cases around everyone else. But collusion is the point at which you start working so closely together with someone else that your code ends up looking exactly the same. And it's a big problem. Please don't do it. And actually, a final note on that is things like Facebook groups and stuff like that. Do not go and post header files to Facebook groups, okay? Because even sharing common header files and stuff, even if it's not the implementation of a code, it's too much information. You need to work individually on these things, okay? I hate dealing with plagiarism. It drives me nuts because it wastes so much time. If you have issues, the course forums are there. Talk to the tutors, talk to myself. If you have confusions about what's the difference between working together just to solve a problem and what constitutes collusion, either talk to me or there is resources available on the university websites. Okay, that's the formal stuff out of the way. Let's go back and talk about multithreading. So today's and this week's lectures are looking at multithreading from the point of view that we're going to do, let me start again. So multithreading, what we're going to do is so far this semester we've written programs that only use one CPU core. And most computers these days you buy have 8 cores, 12 cores, 16 cores. They've each got this different processing core that can be used, but we need to write code that can handle this. Now, can I just get a feeling for the class, who's actually done any multi-threading stuff before? Most people. Who's done operating systems before? Oh, cool, about a quarter of you. People who haven't done operating systems but done some multi-threading, what have you done it in? Like, what do you know about multi-threading? Race condition? Yep. Locks and stuff. Okay, so the first hour of today, we're going to be going into a lot of the theory of multi-threading. Not strictly C++, but going into a lot of the theory of multi-threading. And then the second part of today and Thursday, and potentially the Thursday after the break, we'll be going into a lot of details about how to use the C++ 11 multi-threading libraries. And assignment 4 is going to be a multi-threaded assignment. And after the break today, I might show you what that might look like. So this is all theoretical stuff, so single-threaded programs. So everything we've written so far this semester has been single-threaded. That means it has a singular call stack, and a call stack is how the programs work in terms of calling functions. And so when you call a function, everything that was in the previous function gets paused, gets put on this call stack, and the new function goes to the top of the call stack. When that function returns, the call stack gets decreased. Okay? And what this means is only one command can execute at any given time. So this diagram here, and by the way, I'm going to do a whole lot of hand waving, so you people who have done operating systems, tell me if I get it wrong, but I'm not going to be completely theoretically precise on this stuff. I'm going to do a lot of hand waving just for the general ideas. Okay? So if you look at this, pretend it's some sort of graph, the call stack increases the higher the value, for more things on the call stack, and time is increasing in this direction. And when our program comes in, main becomes the first frame on the call stack. Inside main, we call function 1. Function 1 then goes up on the call stack and happens and keeps it running. Now, function 1 then calls function 2, and so function 2 now goes up on the call stack. You'll notice that once function 2 is on the call stack, okay, what's going on here is main and function 1 are suspended until function 2 returns. Okay? And it has to decrease in the same order. You can't suddenly have function 1 returning until function 2, which was called out of function 1, returns. Okay? So the call stack works very simply. It's every time you call a function, it goes up, and every time you return from a function, it goes down. Okay? That's a single-threaded program. That's what we've done all semester. That's what you would have dealt with most of your course so far. But modern CPUs, okay, just about every single consumer CPU you have today, are either multi-threaded or have multiple cores. Now, there is a difference between having a physical separate core and being able to just run multi-threaded applications on a single core. That's hardware-related stuff, things like hyper-threading and stuff like that. I'm not going to go into that detail, but basically most CPUs these days, including phones, GPUs, physical computers, tablets, etc., have multiple cores or multiple ways in which they can calculate things at the same time. There is differences in the hardware architecture of how these things work. Again, we don't need to talk about that in this course. Okay? The short version of what this means is we can execute multiple things at the same time in parallel. Again, in consumer systems, we often have dual or quad core CPUs. My laptop here is a quad core CPU, which has hyper-threading, which means that when I go to write code, I can do 8 things in parallel. Okay? But hyper-threading, again, is slightly different to having physical hardware cores at different. GPUs, so graphical processing units, can have thousands of cores. They work differently though. So a GPU as architecture is different to a CPU. And so even though they can have thousands of cores, generally all those cores are operating the same instruction at the same time. Okay, so there's languages like OpenCL, CUDA, which allow you to do really fast operations at the same time. They're all the same. Okay, so GPUs are very good at matrix multiplication, matrix addition, whereabouts you've got lots of parallel actions that all need to occur. Whereabouts consumer-based CPUs, again, what we're going to be looking at, you can do completely different actions at the same time. So if you're thinking about graphical user interfaces in games and stuff like that, you might use one CPU or one core or one thread to go and calculate some AI stuff. You might use a different one to be reading input in from a keyboard. You might be using a third one to do some just general game running stuff. You might have a fourth one that's doing some networking stuff, and they're all talking together. That's a CPU. Okay? Again, GPUs are different, okay, but they're still the same idea. Okay, and programs that use multiple threads can be many times faster than single-threaded programs. Okay? Not all the time, but most of the time they can be many times faster. So in C++, each program begins with one thread. Okay? We can use the thread library in C++11 to create extra threads when required. We can choose to start up in parallel and then come back to a series, and then parallelize, and then come back. Okay? Each thread, when it starts, has its own call stack. Okay? So we saw the diagram before, whereabouts we had the singular call stack. When you start a new thread, it has its own call stack. Okay? So consider this example of a single-threaded program. Okay, this is different to the example before. Whereabouts, what we've got is we've got function 1 and function 2. And function 1 and function 2 are unrelated. Let's say that function 1 is going and modifying object A. Okay, so we've got a Euclidean vector. Okay, function 1 is dealing with the Euclidean vector. Function 2 is reading some instructions from a file to do assignment 1. So we've merged assignment 1 and assignment 2 for argument's sake. And so function 1 is dealing with assignment 2, and function 2 is dealing with assignment 1, completely unrelated functions. Now, if this is running in series, we can't run function 1 and function 2 together. We have to run function 1 first, and function 2 has to wait for function 1 to return before it can be called and before it can run. So our call stack might look like this. The main comes in, function 1 gets called, function 1 returns, goes control returns to main, function 2 then gets called, returns to main. And so there's quite a lot of time involved in this process. Okay? You can think of these things as being discrete time steps. Okay? And so given that function 1 and function 2 are completely unrelated, don't talk to each other at all, this becomes very easy to parallelize. And so a parallelized version of this would look a bit like this. We have the call stack come in to main. Main goes off, and before function 2 gets called, it creates a new thread. And that new thread starts up and calls function 1. In parallel, main also keeps running, okay? So whereabouts normally, when you think of a single-threaded program, the instant you call something, everything that follows below that code stops until that function returns. In multi-threaded code, all the code below keeps on running, okay? So main starts up, runs function 1 in a new thread. At the same time, then it can go and call function 2. And so function 2 will run and return, and at some point when function 1 has finished, its separate thread of operation will terminate, and basically these things get joined back together. Again, I'm hand-waving a little bit because joins are a particular technical term that we'll get to. Okay? And if you think about these discrete time steps, on the previous slide, this took 5 discrete time steps. On this one, it took 3 discrete time steps because we did things in parallel. So we sped up our program. Everyone following so far? It's probably really boring to the people who have done this stuff before, but these concepts are important. Okay, so there's common workflows or workloads in how you design code and how you tackle particular problems. Each problem that you tackle, be it building a Euclidean vector, but building a calculator like in assignment 1, building a graph in assignment 3, using the graph in assignment 3, each problem that you tackle in computer science will have a different way to solve it. Sometimes they've got multiple ways to solve it, and you still have to trade off and work out what one's the best. But each problem will have a different way of solving it. And so some problems are inherently sequential. for instance, random number generation. Does anyone know how a random number generator works? Anyone? Oh, nobody. I'm surprised. Okay, so when we talk about random number generation, what do we need to give a random number generator to get it started? We need to give it a seed. Does anyone know why we need to give it a seed? Okay, because it's deterministic. So a random number generator, there's lots of different random number generators, but it's actually very, very difficult to generate truly random numbers. Instead, there's a mathematical function that gets called, and there's lots of different ones. There's a mathematical function that gets called that calculates out a pseudo-random number. The reason why it's pseudo is even though it appears random, it actually comes off a sequence. And the way in which random numbers are generated is they're based on the calculations of the previous random numbers. And so when we give a random number generator a seed, we're telling start at this particular sequence in the step. And so that's why if you give a random number generator the same seed multiple times, it generates out the same sequence of random numbers. Because they're not random, they're based actually on a sequence. And so a good example of a sequential program that is very hard to parallelize is a random number generator, because if you parallelize this program, what would happen is on each of the threads, you would end up getting the same random numbers out because they just all have the same previous sequence going on. So this particular workflow of random number generation is very inherently sequential. This problem has to be sequential. It can't easily be anything else. I'm hand-waving because there is whole studies into how we do this in parallel, but it's a very sequential problem. If you think to even doing things like A-star searches and stuff, they're also very much inherently sequential because you have a queue of stuff that needs to be popped off and be dealt with. You can parallelize things like A-star searches or depth first or breadth first searches, but you still then have this problem of communication, of when do I stop? If I've discovered a solution, then how do I tell every other thread that I have found it and they need to stop calculating? Okay, so there's a lot of problems that are inherently sequential. Having said that, there's a whole lot of programs that are inherently parallel. And so an instance of this can be compressing a file. Does anyone know how file compression works? Or JPEG compression? One person. Good, we're improving. So when you compress a file, think of a file just being a long series of ones and zeros. And you can compress a file in the easiest way by just going, instead of going, oh, I need 100 ones in the next sequence. Okay, because there's 100 ones, even in bits, there's going to be 100 bits. Can I just store a singular one and then store the value after that being, this is the number of bits that are going to follow that have exactly the same sequence. So compressing a file, there's lots of different ways of doing that. It's not the only way, but that's a pretty simple way. Compressing a file just involves looking for patterns in a data structure and figuring out a way of saying, well, we can repeat this pattern. And this is a short piece of instructions for how we repeat this pattern. This thing can be easily parallelized because you can split that file up into chunks. You can process each chunk of that file independently, compressing parts of it at a time, and then just joining the chunks back together. Now, I'm hand-waving because, again, there's ways in which you can do this in different ways. But this is very much an inherently parallel operation. The only sequential bits that's needed is basically joining the file back together at the very end. Okay? Does that make sense to people? The other things to do with parallelization is things like matrix multiplication, lots of mathematics. Now, that parallelized example I gave, there still has to be some sort of communication that goes on. The communication that goes on is basically starting up the threads to start with, and then bringing the file back together, saying that we're finished doing this file, let's write it off to disk, let's close the file. Okay, so there's still, in that parallel application, some sequential tasks that need to happen. We then talk about problems which are what's called embarrassingly parallel. And the assignment I'm going to give you is hopefully an embarrassingly parallel assignment. And embarrassingly parallel programs are ones whereabouts you put these things on on multi-processors, or multi-cores, or parallel code, etc., you split this thing up to run completely independently on its own cores, and it goes much faster than the sequential thing. And what that means is, say we had this time, say a sequential program took 10 seconds to run. We might parallelize that into, say, 4 CPUs, and it might just be the case of 10 divided by 4, therefore it was, each sequence was taking 2.5 seconds to run. With the tear up and the tear down of the threads, maybe it'll take 3 seconds to run. An embarrassingly parallel program, instead of taking 10 seconds to run as a sequential program, might only take 2 seconds to run, even if it's got 4 CPUs. And so we talk about a thing called speed up. And speed up is the amount by which a program increases speed as being parallelized. And super linear speed up occurs in embarrassingly parallel programs. And that's whereabouts you increase the number of cores by a linear amount, and your program, not necessarily exponentially, but much more than what it should be, speeds up. And so, for instance, a multi-threaded web server has this behavior. A multi-threaded web server, what it does is you send in a connection into it, and you get a whole thread basically dedicated just to talking to your computer. Somebody else connects to that web server at the same time, they get spun off in a whole separate thread that does all the communication with them, does all the image processing, does all the PHP scripting processing. I'm hand-waving here because it depends on the exact architecture, but this is particularly how the Apache web server works. And so it doesn't require any communication between threads, because this one thread on the web server is talking exclusively to you. At the same time, it can process out and handle something completely independently with somebody else. There's no communication required between the threads. And so I'm going to walk out and give a bit of a demonstration, but I can come over, I'm going to look at you. I can have a conversation with you, and I can be talking to you about that weekend sort of thing. And at exactly the same time, and I can't do this because I'm a human, but at exactly the same time, I can be up here, and I can be talking to you about how you failed your exam or something like that. Sorry. And whereas as a human, I can't handle that completely separate information, but what he did on this weekend, and what you did over there rolling your exam, okay, has got nothing to do with these guys. They don't need to talk to each other. I don't need to, in my superhuman mind, even cross that barrier, okay? But that's how these embarrassingly parallel programs can work, okay? Now, the assignment, when we get to it, the assignment is an embarrassingly parallel, the assignment's in between a parallel and an embarrassingly parallel problem. It's embarrassingly parallel because you should get some sort of superlinear speed up. Having said that, you will still need to do some sort of communication between the threads that are going on. Again, we'll talk about more about the assignment when we get to it. Okay, let's talk about memory model. So we're still on track so far on Simon. Are we still on track at this point? Everyone's following? Yep, Simon. Yep.
What happens when you try to multi-thread a single-core machine?
What happens when you try to single-thread a multi-core machine? I have deliberately left these.
Multi-thread a single-core.
So, you want to multi-thread a single-core machine. I've deliberately left this stuff out, okay, because just about all systems at the moment are multi-threaded, okay? The short version of if you try to multi-thread a single-core machine, the better question actually these days is what happens if I try to start more threads than there are cores available. So I have a dual-core machine, and I start to try to queue up 8 or 10 things in parallel to happen at once. What happens is some of that processing happens, and depending on your operating system, your program might just get sleeped. It might just get paused in the middle of execution, and something else pops up, and that might get sleeped. And in the middle of execution, it might go away, and something else might get sleeped. Has anyone on Linux ever used the command uptime before, or looked in detail at top? So let me just bring up my laptop. Okay, yeah, I can do this on both projectors. So this here, I'll show you something straight away. Okay, if I cat proc CPU info, does that come up on the screen? It has. Okay, this tells you all the information about for CPUs available on this machine. So what I have is I've got, okay, here we go, let's start down here. So I have i7 computer, 2.4 gigahertz. This is processor 0, okay? And this tells me some technical information about it, okay? I have processor 1, it's exactly the same, okay? I have processor 2, which is actually a third processor, and it's exactly the same. But what you'll discover pretty quickly, and oh, here it goes. Okay, so if you look at this data down here, these core IDs and these CPU cores, even though my computer reports that it's got 8 cores, it realistically has 4, which is correct there. And these core IDs, these physical IDs, are telling me which of these 8 CPUs I'm using. So this next one I come down to, I am now on, you see these zeros here on APCI IDs? This is now number 1. You come down here further, these guys are number 2, and see how the core ID from 1 there, so that's 0. You see how this one moved to 1 up here, okay? So what's going on is this is giving me a whole lot of technical information about my computer to start with, okay? So we've discovered that I've got 4 physical cores, I've got hyperthreading, therefore it's reporting 8 CPUs, or 8 processors, okay? 1 CPU, 8 processors, 4 cores, both of them are hyperthreaded. If I run top, and top just gives me some information about processors that are running on my system. If you look at the top of the screen, you'll see this thing called load average. What load average is load average is the amount of processing my computer is currently doing over the last second, over the last minute, and I think over the last 10 minutes. Load average tells you how much of a singular core I'm using. So if my load average exceeds 8, I basically end up with my computer slowing down because it means that I'm trying to do more than my computer can handle. You'll also see these CPU percentages up here, okay? These CPU percentages are a percentage out of a singular CPU. So I can actually have my computer on a single process go up to 800% CPU, and it's still running on that physical hardware. At the point at which it exceeds that 800%, then things are basically slowing down. Having said that though, when that starts to exceed anything above, say, 4 CPUs, even half my processor usage, my whole computer starts to slow down because my whole computer is still trying to run GNOME and Chrome and a whole lot of other stuff in the background. Okay? So it's not necessarily a good idea. It's not necessarily a good idea to just max out the whole 8 CPUs just because you can. Because what you'll find pretty quickly is your computer will either slow down or crash. Because it will either run out of swap space. Swap space is when stuff's coming in and out of memory. There's lots and lots of issues that can happen. I thought I had it loaded, but I don't. So over a break, I'm going to quickly load some files onto this particular teaching account and show you the performance of assignment 4 and what sort of things we'll be looking at in terms of these sort of performance issues. Does that sort of clear up that? Yep, cool. Okay, so let me switch back and talk about memory. Okay, so we've talked about performances in terms of CPUs. We have talked about different ways of solving problems or different types of problems. In addition to multi-threading involving just the cores of your computer, just the CPUs, memory is also a huge issue. And so, depending on the particular threading library that you're using, there can be different memory models that are involved. Shared memory is when all the threads, all the individual pieces of operations of your program are sharing the same piece of memory. And that shared memory can be globals, or it can be classes, it can be lots of stuff. By default, C++ uses shared memory, okay? If you're used to using OpenMPI or some other threading libraries, this is different. So shared memory is whereabouts there's a big collective piece of memory that everyone's sharing, okay? I'm going to walk out and talk to my friends again, okay? Okay, so I'm talking to him still. If I'm dealing with shared memory, him telling me about his weekend, and him telling me about his exam up here in my memory, I can share that data. Okay, they still might not be talking to each other, but up here I can share that data, so I can sort of act as a go-between. He can tell me something, and I can pass it on to him. Okay, that's shared memory. Okay. Now it's important that when you're sharing memory, that you don't reading from it at the same time is fine. Writing to it is a huge issue. If I write to the same piece of memory at the same time off two different threads, and we're going to go into details about how this happens, then I can end up with memory corruption at best. At worst, I end up with some sort of undefined behavior and basically still some sort of memory corruption, and I'm not aware that memory corruption's happened. Okay? And so the way in which that shared memory can happen is I can come out here and I can ask you to tell me what your birthday is, and I can ask him at the same time to tell me what his birthday is. Maybe I can only, up here, still one birthday at the same time, and so I must still this guy's name and your birthday instead and get that information confused. Okay? So writing to the same piece of shared memory is a really dangerous thing. Local memory is whereabouts you have exclusive memory that other threads can't access. Local memory, in the same way as local variables and stuff like that, in C++ is normally limited to individual threads. Okay, so going back to the example we had before with function 1 and function 2, function 1 and function 2 might have some shared global memory, but inside them, anything that's declared inside function 1 and function 2 is local to it. Okay, and so that means that other threads can't access that local memory. There's this idea of message passing, which we'll talk a little bit, probably maybe Thursday if we're lucky, otherwise Thursday after the break, to do with message passing and futures in C++11. But has anyone programmed OpenMPI before? Nope. Okay. So message passing often happens on big cluster computers. And message passing is whereabouts you separate something out to do some calculation, and these threads, once they've finished calculating, they don't actually necessarily even stop running. What they do is they send a message of memory between different threads. Okay? And that message passing can be used to share data, to share memory, without this whole need for this global shared memory model. Okay? It gets quite complex very fast. There's whole books, whole courses that you can do on this sort of stuff. Okay? We're going to focus a lot on the shared memory and the local memory. We'll mention message passing a little bit. And again, how you approach assignment 4 is up to you. When we talk about assignment 4, you could do message passing if you wanted to. I've done a combination of shared and local, okay? But assignment 4, when we talk about it, the short version is you're just going to be building a sort. You're going to be building a parallel sort. And so you're just trying to sort some numbers as quickly as possible. And you can use whatever tools, provided C++11, you can use whatever tools you want to, okay? So, how does this work in the hardware? This is what most modern CPUs look like, okay? So say my Intel i7 sitting on this laptop here, this is what my memory actually looks like. Each of these CPUs, okay, you can think of as being a core, okay? So you can substitute the word core in for CPU there, okay? So this diagram has 3 CPUs, okay? Or it might have 3 cores. Now again, on the hyperthreading, you might be able to hyperthread these cores. So this is either a 3-core system or it could be a 6-core system if it's got hyperthreading. Each of these cores, each of these CPUs or these cores are connected into what's called a system bus or a cross-bus switch. That's just a, again, I'm not a hardware guy, but it basically is physical, not wires, but not wires these days, but basically some physical hardware that connects the CPUs up and can transmit messages along the system bus. Your RAM, your RAM is shared memory. You might have an 8-core CPU with 8 gigs of RAM. It's not that you have 1 gig exclusively for each CPU, okay? This shared RAM, of course, is shared across all those CPUs. Cache memory, okay, which is missing from this diagram, but cache memory is exclusive to the CPUs themselves. Okay, so each CPU will have a little bit of cache memory on it as well. In terms of performance, cache memory is highly, highly, highly effective. It's very, very, very fast because it doesn't have to go through the system bus. It doesn't have to go down and talk to the shared RAM memory. Okay, very fast, but RAM memory is about 50 to 100 times slower. Okay, I'm hand waving my figures, but 50 to 100 times slower you can think your shared RAM memory is. Reading and writing from a hard drive is about 1,000 times slower than RAM. So you do not want to be reading and writing from your hard drive except for basically when you're reading and writing files. Okay? Now you also have input-output, which is, say, your video monitor feed going out to your monitor, your keyboard coming in, your mouse coming in, etc. That all comes in on the cross-bus switch of a system bus. Are we clear about that hand-wavy architecture of how that stuff works? Because the next few slides, again, we're going to start to get into more detail of what can go wrong with all the system. This is your common consumer multi-core CPU. Okay? This is not what a cluster computer looks like, and it's not what your GPU looks like. Okay? But this is the common architecture for your i7 or your AMDs sitting inside your consumer laptops. This is different, actually, from your Androids. Your Androids are running an ARM processor for architecture, and exactly how it's set up is different again. Okay? It's similar, but it's different. So let's talk about atomic operations. So an atomic operation is some sort of operation, some sort of add or subtract or load from memory, or some sort of basically low-level command on the CPU that normally takes one clock cycle. So a clock cycle, again, you talk about CPUs in terms of, say, gigahertz. That's the number of clocks or ticks or number of things that they can do at any one moment per second, basically. And so high-end computers, they can do many thousands, if not sometimes millions of things per second, but an atomic operation is a singular clock tick. It's a singular thing that can happen at any one very precise moment in time. Okay? Now, most memory writes, so you write something into memory, are atomic. They actually might take more than one clock cycle, but they happen in one sequence that can't be interrupted. So let's talk about just this very simple command called I++. Okay, so we're going to get I, we're going to increase I by 1. It could also be plus plus I. For the sake of this example, it's doing the same thing. Okay? So what does plus plus I do? What do we think a plus plus I does? Read the value and then increment it. Okay? Now, in terms of what's actually happening on the CPU at this point, or in the machine code, you might have that value I sitting inside RAM. Now, remember, RAM's quite slow. Okay? And the CPU can't operate on RAM. CPU can only operate what's inside its physical cache on its physical chip. And so what happens is you get the command I++. Step 1 is you load that value of I from RAM into as a cache register on the CPU. Okay, so registers, everyone know what registers are? Anyone not know what a register is? Okay, registers sit inside your CPU on the cache. Okay, you load this value of I into register 1. That might take one clock cycle. You then, in cache on the CPU, increase that value inside that register. Okay, so inside for RAM, the old value of I is still sitting there. Now on the CPU, we've increased that value, which we copied across into our register on the cache, by 1. That's a second clock cycle. Step 3 is we store the value from register 1 on our cache back into that memory location in RAM. So we write that back out to RAM. That might be a third clock cycle. Again, I am hand waving, but this is roughly how it works. Okay? And so you can think of your CPU and your cache registers being as that one physical unit there. The RAM's over here connected by the system bus. Okay? So each machine instruction, remember our code gets compiled down into machine code. Each machine instructions typically take one clock cycle. And only one thread, or core, can write to a specific memory address each cycle. Okay? but they also might be able to write to different memory locations, and writing to different memory locations is normally fine. Okay? Everyone with me so far? Because this is about to get technical. If it wasn't technical already, it's about to get more technical. Everyone with me? Cool. Let's talk about race conditions. So, consider this. And I'm going to go to a live demo of this working in a minute, or not working. Consider I have int I is equal to 1, okay? I then have two threads of operation. Thread 1 wants to increase I. He wants to just keep on calling I++, okay? Or just actually wants to call I++ once. Thread 2 wants to decrement I, wants to decrease I minus minus, okay? These commands, in terms of C++ commands, might be reduced to these machine instructions. Step on thread 1 to increase I, it might be load value from RAM, increase the value, store from RAM. Okay? For decrement, might be load from RAM into register 2, by the way. So the first thread was dealing with register 1, this one's dealing with register 2. Or this could also be register 1, just on a different CPU. Doesn't exactly matter for this example. Okay? But this load from RAM is going to two different cache locations. This one's increasing its value in its register, this one's decreasing the value in a different register, okay? This one is then writing out to that memory location, that one's writing out to that memory location. Now, on the previous slide, I just told you that only one thread can write to memory at any one moment. So only one thread can do this last step at any one moment. One of these things is going to have to wait for the other one to finish because they're both trying to write to the same memory address. My question to you, and again people who've done operating systems should know this, is I started with I is equal to 1. One of these threads increased I, one of these threads decreased I. What is the value of 1 after this code is run? 0 or 1 or 2. And we don't know which it's going to be. We'd expect it to be 1, okay, but it might not be. So there's 3 different outcomes that can happen, okay? Case 1. Because writing to memory address is atomic, okay, what can happen is thread 1 might go and execute all 3 of those commands first, and thread 2 might go and execute all 3 of those commands second. And so what happens is we loaded the value 1 in, we increased it to 2, we stored it back up to RAM. Then we loaded number 2 in, we decreased it back to 1, and we wrote it out to RAM. We increased, we decreased, it's still 1. That's what we might have hoped to have had happened. Might have hoped. Okay? Solution 2 could be this way around. Thread 2 went and did its thing first, and thread 1 got the solution. Okay? And so what happened here is thread 2 loaded in value 1, decreased it to 0, wrote out to 0. Thread 1 loaded in 0, increased it to 1, wrote it out. Okay, that's fine. Okay, so that ordering, like that, doesn't matter. Let's see what happens if they run at the same time. Remembering that only the write out to memory is the bit that needs to be completely atomic. Okay? So if we do the increment and the decrement in parallel, this happens. Thread 1 goes and loads the value 1 into its register. Thread 2 also goes and loads the value into its register. Thread 1 increases 1 to 2. Thread 2 decrements 1 to 0. Okay, that's fine. We've got 2 copies of these things. Then, because this writing is atomic, let's just say that thread 1 went and wrote that value 2 into memory. And then this one goes and writes its value 0 into memory. Suddenly, I++, I minus minus on 2 threads is 0. Okay? And this is a problem because it's not the right answer. Okay? And I'm going to show you an example of this happening. Okay? Let me see what the next screen is. No. Okay, so next screen's got some code on it. Okay? I don't care about the code too much, but let me just quickly show you. I've got my value I. I am going to iterate 1 million times I'm going to iterate 1 million times. Thread 1, okay, I'm doing this as a lambda function, but thread 1 is incrementing 1 million times. At the same time, thread 2 is decrementing 1 million times. At the end of this function, I am printing out the value of I. Okay? As a side note, don't compile this for optimization flags turned on, because the optimizer is smarter than I am, and we'll figure this out. Okay? But let's go and do this. So I'm going to leave up on the screen at this point. I'm going to leave up on that screen. Oh no, I'm going to leave up on one of these screens, that code. And let's bring this up. Okay. Let's try this. We'll get to that. We'll get to what join means. Okay, so there's my code. Okay. And I'm going to now make, it's called thread lambda race.cpp. Okay. I'm going to run this. Now that's not 0. Let me just clear this so you can see this. Okay, that's not 0. That's not 0. Oh, that's 1. Okay, so that time it worked. That time it didn't. That time it didn't. That time it didn't. So as you can see, what's going on is this issue. Oh, we've got 1. We've got 1 again.
Do you think this is normally distributed?
Do I think this is normally distributed? In terms of the numbers coming out, is this normally distributed? No. It is not normally distributed. This output here, okay, so the question to do with normal distribution is to do with numbers coming out. Does this follow a bell curve? No. Or I don't know, but I'm going to go with argument no. This output here is purely dependent on what is going on the rest of my computer at the same time. Okay, so sometimes you're getting the value 1 out because obviously my computer's doing so much stuff maybe at the same time that it's all being pushed off to one CPU and the stuff is just having to run in series. At other times it's doing bits and pieces of it. One of those threads is running a lot faster than the other one, and this race condition, okay, so these things called race conditions are occurring. I would not believe that this is randomly distributed. At best it might be uniform distribution. But I simply don't know. It could be many different things. You could write some code and figure this out if you wanted to, but I highly doubt this is normal. Okay? So we've got a problem. Everyone can see what a problem is, right? Okay? So, what's the time doing? Okay. So, how we deal with this, I'm going to stop in a few minutes, okay, but just to get the rest of the concepts out of the way. How we deal with this is what's called a critical section. Oh, let's go look for computer screens back. Okay, so what we want is we want the machine to deal with these 3 machine instructions all with one block of operation, okay? This block of machine instructions is called a critical section. The reason why it's a critical section is all of this has to work in sequential order like this, otherwise you end up with these problems, okay? A mutex, or a block of mutual exclusion, allows us to let only a single thread access a critical section at any one time. Okay? So we've got this problem. We want our code to be run in parallel all the time, but with shared memory, we end up with problems. And so we want to identify some pieces of code that says only one CPU can access this block of code or this piece of memory and do this operation at any one point in time. Okay? So a mutex is a lock type object that is shared between threads. So there's one mutex per, well, not necessarily per critical section, but there's one mutex object, or there can be multiple, but think of a mutex object as something that we can say, if I have, say, ownership over a mutex object, it means that I can run this critical piece of code at that point, and then when I don't need to run that, I offer mutex up to whoever else needs to do it, okay? So mutex is actually an object in memory that the threads share, and one of them takes ownership over this mutex. We're going to go into detail of more of how this works soon, but one of these threads takes ownership over mutex, runs its critical section, releases the mutex back out, okay? And so this, with mutexes, prevents these race conditions from happening. Having said that, you need to identify in your code where these race conditions could happen, and then build mutexes around it. So it's not as simple as, oh, I just go put mutexes everywhere, okay? Mutexes also slow down your code because it means that only one thread can access that particular code at that particular point in time. Okay? So we've got this trade-off here. We're trying to make our code fast, use multiple threads. At the same time, we need to make sure our code gets the right output. Okay? So critical sections, mutexes, we're going to go into detail about how these things work when we get to the proper C++ code for this stuff. So a mutex acts as a lock. Okay? A mutex acts as a lock. You lock the mutex when you want to go in and execute a critical section, you unlock it at the end of that period. Okay? So if the second thread wants to lock the mutex while some other thread has already locked it, what happens is two things. Firstly, the other thread can just go, oh, well, forget it, I don't want to deal with that piece of memory anyway, I'm going to go off and do something else. That's actually quite an effective way of keeping your code running in parallel. It just goes, oh, I can't lock that, okay, I've got a backup plan and I'm going to go execute it. That way of coding, though, can be very difficult to run. So normally, the second thread that is trying to now lock this mutex while a different one has got locked just sits and waits, busy waits. It just sits there and goes la 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 until the first thread comes along and goes, oh, I'm done. And then the second thread is able to go, good, now I can take the lock and I can go do my thing. Okay? But forgetting to unlock mutexes is a major source of bugs in your code. Forgetting to unlock mutexes is a serious source of bugs in your code. There's a reason why this is in red, because I'll give it away right now. You have a question on this in the exam. You have a question on mutexes in your exam. Okay, you haven't got much on multithreading, but one of your questions is to do with mutexes. It is to do with the bugs that mutexes might happen, and unlocking is a major source of bugs. Okay? Now, you can also do really dumb things, like the whole idea of a mutex is only like a convention. It's only going, okay, this is a way of preventing this issue from happening. But mutex objects, they use memory, and they can be problematic themselves, like forgetting to unlock the mutex. So you can just write code that just doesn't use mutexes, or just goes, oh, the mutex is locked, oh, stuff it, I'm just going to write to that piece of memory anyway. You can do that. But this is very, very, very dumb. Mutexes are designed to prevent critical sections from hitting race conditions. Okay? So you should always, well, you shouldn't always use mutexes. We'll use something better than mutexes when we get to talking about code. But mutexes, or the idea around mutexes, you should use. Okay? Okay, in terms of locking, I'm seriously going to take a break. I'm just trying to get to a good point to stop. Okay? In terms of locking, okay, so we've talked about mutexes. We've gone, mutexes are really great, but you have this problem of locking and unlocking. Deadlocks are major sources of bugs in mutexes. The reason why deadlocks are major sources of bugs is whereabouts you end up locking one thing and also needing to acquire a second mutex that somebody else got locked. And so you wait for him and he waits for you. An example of how this might happen is consider that you have two shared objects, object A and object B, Euclidean vector A, Euclidean vector B. You have two shared mutexes over those Euclidean vectors. You have a mutex for dealing with Euclidean vector A, you've got a mutex for dealing with Euclidean vector B. Thread 1 wants to come and call the function standard swap on A and B. Thread 2 wants to come and call the function standard swap on B and A. Okay, so they both want to do something that modifies both Euclidean vectors. Okay? The code might look like on the screens. You call mutex A.lock, you call mutex B.lock, and then you call standard swap on A and B, you unlock the mutexes. Thread 2 might go and do exactly the same thing, but because it wants to swap these in opposite order, it locks B first, locks A, calls swap, unlocks, and unlocks. What's the problem with this code?
One is going to lock A, and two is going to lock B.
Yep.
And then they're both going to try and get the unlock, but they won't be able to until the other thread releases the lock.
Yep. Yep, that's exactly right. So thread 1 is going to lock A, no issue. Thread 2 is going to lock B, no issue. Thread 1 is going to go try and lock B. Well, B is already locked, so it's now going to wait for thread 2 to release that lock, but thread 2 is trying to now lock A, and he's now waiting on this one. This is called a deadlock. Deadlocks are really bad and very hard problems to avoid. The reason why deadlocks are very hard to avoid is because in this example you can kind of see it happening quite easily. In real code, deadlocks are much harder to even identify, and there is ways, and again we'll talk about this, again it probably won't happen until Thursday or later, but there is ways to avoid these, or try to avoid these issues, but they're a big problem. Okay? So again, deadlocks are a major source of bugs, and they're not easy to test for. So critical sections, you identify you've got a critical section, you put a mutex onto it, problem not quite solved, but basically problem solved. Deadlocks are not easy to test for. They're not, you can just set up, like I've got my example of my critical section problem, like that with the registers. I can't easily go and write some code to deadlock for you. They're very hard to actually set up proper test cases for, okay, but they're a major source of bugs. At this point, let's take a break for 5 minutes. Does anyone have any questions? No? Okay, so this is all the theoretical stuff. We'll go back to C++ in 5 minutes' time, okay? Okay, so we're going to resume, and I'm going to resume by talking or showing you a little bit of assignment 4. Now, assignment 4 for spec hasn't been written completely yet, okay, and I'm kind of holding off writing it and releasing it because people are having so much issues with assignment 3. But to get assignment 4 in your head, okay, this idea of this parallel sort, what you're going to be doing is, I've created just a file off the top of these screens here, okay? And I have some numbers up the top of these screens. So 1, 43,542, 64,000, 2,001, 73, 3,000, okay? And what I want to do is I want to sort these numbers. Now, the type of sort that we're going to be doing is not just a sort by your standard sort these in increasing order. What I want to do is what's called a bucket sort or a radix sort. And this sort is sorting the numbers by the starting digit, and then after sorting the numbers by the starting digit, so say you've got, do I have an example here? Yeah, let's throw on an extra number to show you what I mean. Okay, I'm going to throw the number 10 into here, okay? So I want to sort based on starting digit to start with. And then the second thing I'm going to do is I'm going to sort based on the increasing value within those numbers that have the same starting value. And so in this instance, with this sequence of numbers like here, the correct output of this is 1, 1, because 1's always starting, and then 10, okay? Because 10 is larger than 1 and 1. But then 2,436, then comes next because it starts with 2. Then the values that start with 3 come, and then the values that start with 4 come, and the values that start with 5 come. And so if I put the value 50 into here, okay, 50 is going to come down here before 542. So this is a 2-step process. You've got step 1 of figuring out what the first digits of the numbers are, and step 2 is then putting these things into buckets. So all the numbers that start with 1, put them for number 1 bucket. And all the numbers that start with number 2, put them in number 2 buckets. All the numbers that start with number 3, put them in number 3 buckets. And then sort those buckets and then plug all the data back together. Hint, hint, this problem is inherently parallel. Okay, because you can use basically 1 CPU core per bucket. We're clear on this idea so far. Okay, this is going to be written up more into a spec, okay, but we're clear about how this sort's working, okay? So what this code will look like is I am actually going to give you, let me just show you maybe even this. Nope. So I'm going to give you some starter code for this. And this, oh dear, this starter code That is completely bizarre. Okay, I won't be able to show you the starter code right now. I don't know why that didn't work. Bucket sort. No, oh, yeah, sorry, it's HPP. Oh, okay, say single. That might help. Okay, so I am going to give you some starter code. This is for assignment. This is the whole assignment for that type of sort written as a lambda function. Okay? You guys have to go and figure out how to do this in parallel. Okay? I'll give you a giant hint. It's not just make that thing run across 10 different threads. Okay? You will also be given a header file. Okay? Your header file at the moment might just look like this. Okay? See, it's just got this vector. By the way, note this is a struct and all these things are public. The reason for this, we're trying to write fast code, so we're going to ignore all the object-oriented, make all your data private stuff. We're just trying to go for speed in this assignment. So the struct is just a public thing with some public numbers to sort, which I write into, and then I call as the sort function, and I'm going to tell you in the sort function the number of cores that you should be using. You can choose to ignore that if you want to. Okay, you can choose to ignore that if you want to. My hint is do not ignore that, but you can choose to ignore that if you want to. And you need to implement sort. So this is the single sort version is the starter code here. Now there's lots of different ways of making this work. Okay, and you can modify both. You definitely need to modify the .cpp. You can also modify the .hpp, so you can introduce additional data structures. You can introduce additional functions and stuff like that. My code has 4 or 5 different functions in my final version of my .hpp file. And when you submit, you'll be submitting both a .hpp and a .cpp, and we'll be testing it like the other stuff of compiling a test case against it. The only requirement will be, which will be enforced in terms of the .hpp, is you will need to maintain that vector of numbers, being numbers to sort. Once you've sorted them, they need to be stored back into that correct vector, okay? And you need to maintain that correct signature on that sort function, but you can introduce additional variables, mutexes, etc. as you go. How do we test this? Well, let me show you this. So I have this command called time, which inside Linux I can put on the front of any command. And time just tells me the amount of time that something ran once it's finished, okay? And so if I run the bucket sort here, and this is sorting, I think, off the top of my head, 10 million variables, so it might be 100 million variables. What it's doing is it took 6 seconds to run. It took 6 seconds to run then. Okay, and my testing code actually prints out, to make sure it's working a little bit, it prints out the first value, it prints out the last value, and it prints out some data in the middle. And this data in the middle, I'm just using to check that it's correctly doing this bucket type sort. Okay, so the single-threaded version of this took 6 seconds to run. The multi-threaded version, if I run it, is going to take 0.6 of a second to do exactly the same thing. Remember, I've got 8 cores, and that just went 10 times faster. At best, that should have taken 8 times faster. So it just went 10 times faster. This is the point about these things being embarrassingly parallel. This sort is an embarrassingly parallel sort. Let me run the first one again. This first one's going to take about 6 seconds to run. So we're between 6 and 9 seconds to run. Okay, so it's going to sit there and it's going to churn away. Its things, there it goes, takes 6 seconds. The second one is going to take, bang, 0.6 of a second again. Okay? So this problem is an inherently parallel problem. Okay? But your performance here is going to matter how you use the mutexes, how exactly you design the stuff to run. In terms of testing this assignment, the test will be doing 2 things in a similar way to what we're doing on assignment 3. We will be giving you a certain amount of time to run. So for instance, for this test, I might give you 2 seconds to run. So if you're still doing everything as a single thread, you're going to fail that because you can see how it takes too long as a single thread. If you're multi-threaded, you're going to run that quickly. But what I'm also going to do is I'm also going to restrict your memory somewhat. And so restricting your memory, this is going to be one of these assignments whereabouts I'm just going to keep on giving you more stuff to sort and limiting your memory and limiting your time. And so you'll need to figure out fast ways to use mutexes, to use locks, to use shared and local memory, message parsing, etc., to keep your code going faster and faster and faster. Now, I, at this point, am certain that I can make my code go faster than this again. I've got two versions of the assignment. I'm not going to show you the other version because it's not compiled right this second, but I've got two versions of the finished assignment. One using shared memory, one using local memory. My shared memory version, which is one I'm not showing you, runs this in about 1.6 seconds. My local memory version, with a little bit of shared memory and some mutex locking and things like that, goes this fast. So it's not just a matter of just going, oh, it's parallelized, that can work. It's a matter of, once you've parallelized it, thinking very carefully about what you're doing for memory and how you can make it go fast. Okay? Again, in terms of marking for this, there'll be marks for, first of all, doing it in parallel, and then for high distinction sort of marks will be going, how quick can you make this thing go? So you can have a bit of a competition if you want to. I'm showing you this now so you've got the context of what I'm talking about for the rest of today and for the rest of the week, but don't worry about this too much until after you've done the third assignment, but think about this, okay? Because this is going to influence the rest of what we're talking about. So let's go back to that computer. So when we use C++11 threads, there's a couple of things that goes on. First of all, we need to use the threading header file. Okay, so we hash include a thing called thread into our code. This is a C++11 set of libraries. When we compile, okay, and hopefully this works for you guys who are using Macs and using Windows. If not, you might have some problems that hopefully people can share their knowledge on if you do smack into problems. When you compile, you need to link against a thing called the pthread library. And there's different libraries for how multi-threading works. The C++11 thread library just wraps around a couple of different implementations of proper multi-threading libraries. And so on Linux, we wrap actually against this thing called pthread. Pthread, I'm pretty sure, should work on Windows and should work on Mac, okay? But you might need to check that, okay? So this is the setup that we'll use for the assignment and also for all the code that I'm about to show you over the next 20 or so slides. Now, when we talk about threads, we're going to be able to start new threads of operation on functions and function objects and lambdas and member functions. And we're going to step through how we do that. So this first example is just creating a thread with a function pointer. Okay, so this is how you would have done probably pre-C++11 function pointers for starting some threads. So I have a function here, and you're going to see this function a lot over the next few examples. It's called counter. It takes in the number of iterations. Okay, it takes in the number of iterations, and it goes and increments, and as it increments, it prints out the ID of the thread that's being used. Okay, so when I showed you Linux top before, each individual thread has a unique identifier which is given by the operating system kernel. It gets that identifier, prints it out, and it also prints out the value of I. Now, there's no shared memory in this program. That int I, okay, the int I inside counter is a local piece of memory, okay? But we're going to start two threads. We're going to give it a function pointer, which is just saying counter here. And so the first one we're going to tell it to count 6 times, and the second one we're going to tell it to count 4 times. And don't forget that main is also its own thread, so we can just call counter like a normal function on the main thread, and it's going to run. Okay, so this code is actually using 3 different threads of operation. Okay, there's the main thread which comes in and starts our code, and then we independently start up T1 and T2. Okay, so there's 3 threads of operation going on in this code. There's not 2. okay? And so this one's going to iterate 6 times, this is going to iterate 4 times, this is going to iterate 2 times. Lines 12 and 13, these things are all going to happen in parallel. So line 12 starts executing, line 13 will start up a second thread and start executing, and then line 14 will fire up as well. But now the question before the break was about, well, what does join do? What join does is it stops the main thread and says wait until the previous threads have finished. The reason why you need that join in there is because otherwise the main thread will call its counter function, realize it's finished, go and return, and what happens is when you return from main, your whole program gets executed. And so when your whole program gets closed after returning from main and you haven't joined back up those threads that were currently in existence, best case scenario, your whole program goes and it gets destroyed. Best case scenario, I believe Linux, Mac, and Windows should do that. Worst case scenario, you end up with zombie processes. Zombie processes are awesome. I'm just going to see if I've got any zombies going. No, I don't. Okay, but let me show you again. Bring up top again. Let me show you what these things look like. So again, top is very powerful for telling you what's going on with your computer. If I take a look at reading up the top of here, it says tasks. So there's 393 processes currently running on the system. 393 processes. 394 just now. And so those 393 or 394 processes, remember I've only got 8 cores, okay? So a lot of them will be just working in the background. So at the moment, even though it's going up, now I've got 395. You'll see that there's only 3 that are actively running, and there's 393 or 392 that are currently sleeping. This means that they're just waiting for some sort of input or for something to happen. 0 are stopped. Now I can stop a process. If you've ever used Linux, what I can do is, okay, so say if I go into my single sort tester over here, okay? I run this, okay? Let's try to see how this actually looks. Let me see if I can drag this. Okay, I'm going to have a hard time. It's going to have to be fast. Okay, so I'm going to run this. In the background, I'm going to switch across to my piece of top there. Okay, see how it's maxing out for CPU at 100? Okay, and then it returned. Okay? And so what happened is my load average didn't load up fast enough, but my load average would have increased. That thing maxed out 1 CPU. What I can also do is I can run this again, and I can press Control Z, and this now says that the process is stopped. I go across to top, and top is now telling me I've got 1 process stopped. It's not sleeping. Sleeping means that something is waiting for something to happen, but it's still in some sort of executing state. Something that's stopped is physically the kernel saying, you are stopping, you can't communicate, you can't read or write to memory, you can't do anything. Something is stopped, it does that. I just need to bring this back up, so I bring this back to the foreground, and it starts running again. Something that's a zombie is something that basically inside the kernel of the computer. So you see these PIDs over here, these are these thread IDs, those process IDs, okay? What happens is the kernel's lost control over that particular thread, okay? So in the case of maybe your program didn't cleanly execute, or didn't cleanly exit, okay? And so you've got stuff that's going off and running on your computer without the kernel having much control over it. Normally zombies are okay because even though they're a problem, they're using up a little bit of memory, a little bit of space and things like that. Normally they're okay because it just means something's broken and they get fixed on a restart, okay? So 0 zombie process is good. I'm surprised I haven't got 1 or 2 zombies at the moment. It's pretty standard to see 1 or 2 sitting there. If your code is going into some sort of zombie state, okay, you've probably got a pretty major bug in your code somewhere. Okay, let's jump back. So here's the thread with the function pointer. I'm going to show you how this works in a second. Let me just, sorry, jumping between 2 media computers a moment. Let's just bring up splits of screens. Okay, so that screen's going to have the code on it, and the screen we're going to do some stuff with. Okay, so we're going to make, what are we going to make? We're going to make thread with function pointer. Okay. And we're going to run this, and this runs, okay? And so you can see this thing running here, and it's gone and used 3 CPUs, and it's printed out its thread ID, which is quite a big number. It's printed out for values of initial 1, 0. Then it's printed out 1, and then 2, and 3, and so on and so forth. Now, the reason why this printout is all corrupted, well, actually, who can tell me what's going on with the printout straight away?
Some threads are getting interrupted before the headline prints.
Yeah, so basically we've got not quite a race condition in the same sense, but we've got a critical section going on right here. This output stream should be a critical section. You know, only one thing should be writing to the output stream at a time, otherwise your printouts get all corrupted like this. Okay? But that's not the point of showing you this. The point of showing you this is we have 3 different threads. One of them is increasing by 6, one of them is increasing by 4, and one is increasing by 2. And they're all happening in parallel. Okay? There you go. 17 lines of C++, and we have multi-threaded code. Easy. Right? Easy. You can go to the assignment now. Okay, but note also with the join, okay, so we talked about zombie processes, note also with the join, that isn't always the best approach to take. There is the idea of thread pools, which is basically we have some threads that are constantly running. We have some controller over the top of them that controls when the jobs come in, how to distribute these jobs cleanly. Too complex. I looked at potentially giving you a thread pool to use in assignment 4 rather than just telling you how many CPUs you should be using. Too complex to implement, too confusing. So I'm just telling you how many CPUs you've got, and you're going out and figuring out how best to do it by yourself. Threads with function objects. So remember that we've got functors. And so functors are basically structs or classes that just overload the call operator. And so they can act like functions. And so here's a functor. It's a struct, it's a counter. It contains a variable called the number of iterations. It contains a constructor which sets that value. And then, because it's a functor, it gets the call operator and goes and does exactly the same as what we saw before. Now, we can run this by creating thread 1 that constructs a functor on operation like that and goes and calls it. We can do it with a named variable, okay? So that's a temporary variable, named variable on thread 2. In this particular example, there's only 2 threads that are doing for counting, because this is not just a standard function like what we saw before. Having said that, there is ways in which we can get main to call this as well, which I'll leave you to figure out for yourself. But yeah, so you can do it with some function objects. Note that these examples are taken from a textbook called Professional C++. There's a whole section, a whole chapter in that book about how to go and use a threading library. This is not in the standard textbook, okay? So that's why there's a lot of details in these slides as well. Lambda functions. Lambda functions are awesome because you can just go and create a whole inline or in function that we can use. So no big overarching functions, no big overarching functors. Here is a lambda function defined inside main, which goes off and creates 2 threads and goes and does exactly the same thing. And also with that lambda function, we could also call it out of main by itself just by calling a lambda func, and that would work. Now, there's a couple of things to note with this slide. The lambda function, see, I'm storing the whole function into an auto variable. Okay, lambda functions are cool. I can store a whole function into a named variable. Okay, and the type of that variable is standard function. Okay, but I've got a whole function that's stored as a variable type. Okay, if C++ wasn't confusing enough, it just got better. Okay. So anyway, I've got my function there. I can go out and call that. Okay. does everyone understand what this thing's doing? Okay, because the next couple of slides, this starts to get more interesting with lambda functions. Okay? So everyone understand what this is doing, okay? What's the output? While I quickly go and find the example, what's the output? Who can tell me? How many times does thread 1 print? 10 times. How many times does thread 2 print? 5 times. So I'm expecting 15 lines of output. Well, actually, I'm expecting 30 because they print 2 lines each, but I'm expecting 15 lines of something to have been printed, right? And so there it goes and runs. And actually, in this case, it was perfect output, and bang, it works. Okay? Let's change this function ever so slightly. I have an int number of iterations equals 10. I am capturing, for reference, this is lambda with captures. Okay? So I'm capturing the number of iterations by reference. I'm then firing up thread 1 with lambda function up there. I'm then changing the number of iterations to be 5 and firing up the lambda function the second time. How many times does the thread print? How many times do I get output? Okay, I'm going to come back to that because that was the right answer. What are you guys saying?
Well, I said 10, but now I'm wrong.
Okay, so you see, who thinks that thread 1 prints 10 times? Okay, and then kind of you've realised it's wrong. Why is it wrong?
Because, like, it could be up to 7 or 8 or something, and then num iterations would be set to 5, and because it's using the same variable just by reference, it'll say, okay, well, that's already, it'll compare its I to that, and it'll say it's already greater, so it'll stop.
Yep. So we've basically hit one of these, again, critical sections. Again, this isn't strictly a race condition, but we've hit a critical section, which is the number of iterations is equal to 10. We then call that lambda function, passing in that reference. That starts up the thread and starts going, but then we change the number of iterations to be 5. Because it's called by reference, number of iterations then gets changed down here, and so somewhere between 5 and 10 outputs you get. Somewhere. Yep.
So T1.join should be moved a couple lines before.
Oh, okay. So you're saying I should move T1.join to a couple of lines before. What happens to my program then?
It will wait for the first lambda function.
Which kind of defeats the purpose, right? So moving T1.join higher up and just waiting for that first lambda function to finish kind of defeats the purpose of having this in parallel. Okay? So that's not the solution to the problem. Okay? But what happens? Okay, so what actually might be a solution to a problem? How might we deal with this? Don't pass by reference? Yeah, that is my next slide, but how else might we deal with this? Yep.
You've got a unworked variable that stores num iterations using a...
Yeah, just create a new local variable inside the lambda function that stores a copy of num iteration. So don't copy the reference, copy the value, and that will solve your problem. Okay, so that's a good solution. Now, the other way in which we can do it is don't capture by reference, capture by value. How many times does thread T1 print now? I'm really hoping I've got this example because if I do, I'm going to show you how it works. So how many times, while you work this out, how many times does T1 print in this example up on the left-hand side? So, how many? Read it carefully. I've got the number of iterations equal to 10. I've got my lambda function, which is taking in num iterations. How many times does T1 print? What? Oh, no, how many times does thread T1 print? 10. Does everyone see it? Thread T1 prints 10 times. Yeah, because it's copying. It's a copy. It's not a reference. Okay, we've got that. Okay, because it's important for the next bit. How many times does T2 print? I'm hearing 5s and I'm hearing 10. Who thinks it prints 5 times? Who thinks it prints 10 times? Who doesn't know? Who thinks it prints 10 times? Oh, so who thinks it prints 5 times, and why do you think it prints 5 times?
It should just take in 5 as number iterations and then do 5 things.
Okay, that's what you say. Who thinks it prints 10 times, and why?
Because the lambda function's been made, because we declare the lambda function above when number of iterations is 10.
Correct.
So is that valid?
Yep. So because we're storing the lambda function above, and the lambda function is capturing by value, remember this is capture for parameters are different, so we're capturing at this point, we're capturing the value at being 10 when it's defined at that point. This lambda function is always going to print out 10 times. And I will show you. Here's the code. Okay, so I've got that's for reference version, okay, and I run this a few times and it just keeps on outputting. Unfortunately, I don't have a line count, but trust me, those line counts are changing sometimes, not all the time, but, oh, no, that changed a little bit. But I can run that capture and it's going to, actually perfect. That capture version, see how it's printing out 5 and 5? Okay, so not 15. Let's go and change this one line to change this from a reference to a value. Let's recompile and let's run 20 outputs. Okay? Yep, question.
If you passed our reference, and instead of checking for I less than num iterations,
Yep.
you started at num iterations and just checked that R is greater than 0 and decremented.
Oh, yeah, that would work, I think. Okay, so the question is basically, can we do this? So that's your version. Oops. So this is what you're saying. Just change it around like that. Oh, and decrements. Yep.
Would that solve the problem?
Would it solve a problem? Well, it kind of does and kind of doesn't. Okay? So let's make this and let's run this. Does this solve a problem? Oh. Oh, okay. So does this solve a problem? We still have a huge problem here. Now, we've got 2 huge problems here. First of all, which I was expecting to have happen, the first thing I was expecting to have happen was I was going to go, well, now your output's wrong. I told you to count and increase your count, and you just went, oh, I'm just going to print out for decrease. Okay? And so you would still need to figure out a way to print out the correct value of I. Okay? Because you're now printing out decrementing instead of incrementing. Now, the problem that we've got is that's still printing out only 5 times. Why?
Number of iterations is changing before the for loop.
Correct. Number of iterations is changing before the for loop gets called. Okay? So this is a problem. This is, again, why shared memory is not necessarily evil, but these are the sort of problems that you can face. Okay? So lambda functions are powerful. I love lambda functions, okay, because it allows you to do cool, funky things really quickly, okay? But you end up with problems. Now, what's missing on the slide, and let me just quickly change this code around. Let's go back to the reference version. Let me move this num iterations from that point there to pass it in as a parameter, okay? So I'm just going to say int. Let's pass it still as a reference, okay? Let's pass this value. I'm not quite sure how to do this. Let me just, it might be a comma rather than a bracket like this. Okay, but let's try this version, see if it works. Okay, let's see if that makes, not going to work. Let me try this with a comma. It's not going to work. Okay, so what I'm trying to do is I'm trying to set up a lambda function where it takes in those parameters. In order to get this to actually work, you probably need to use standard bind and create a bind object around this, which standard bind will convert that lambda function into a bind functor and go from there. Too technical, and I'm not doing it in the space of 5 minutes. But you can create some sort of wrapper around that to get you the behavior which you expect. Okay, I'm going to leave that to figure out yourself, okay, if you want to. But let's talk about member functions. Okay, so here I have the same setup again, okay? So we've looked at function pointers, we've looked at functors, we've looked at lambda functions. Okay, let's look at member functions. Okay, so threads of a member function, I have a struct or a class called iterator. I then have this counter function again. This is a member function of that struct iterator. Inside main, I can create an iterator object. I can create the thread by naming the function inside the iterator that I want to call. The address of I being that class, that value to pass into that parameter. I can also just call the same member function object in parallel like that, I count of 5, okay, and that goes and runs. Okay, so that's a member function of a class. Okay? So the short version is in terms of creating threads, there is different ways in which you can do it, and you'll need to figure out which way is the best way. Okay? It will depend on the exact content of your code. Okay, I've got 10 minutes. I'm going to try to get through this next section, and then we're going to pause and pick up mutexes on Thursday. But let's talk about atomic operations. So we're talking about atomics, and atomic operations inside C++ are basically whereabouts it can do things like increment and decrement. It doesn't cause race conditions. And so there's a thing called the atomic types library, and these provide primitive type versions that are atomically correct, okay? So what we can say about these things being atomically correct is, say, an atomic int, or atomic unsigned int, or atomic long, is one of these types that correctly is able to increment, decrement, read and write memory without being corrupted if it's used in parallel. Okay, so we've got this atomic type library, okay, that the C++ standard provides. You can go read about it yourself, okay? I'm telling you about it because we're not going to use it, but I'm still going to show you and then show you some problems with it, okay? And so let's take a look at this. Let's go back to our plus plus and our minus minus example. This plus plus and this minus minus example, okay, the problem that we had was with the race condition. We had the problem with the race condition. And so the previous version of this, if I can just quickly find it again, thread lambda race, it should be called, there it is. Okay, so this is the old code and that's the new code. It's exactly the same with the exception that for int I equals 1 up the top has been changed to an atomic int. Okay? This atomic int will always print out 1. And I believe I have, yep, thread lambda atomic. So here it is, okay? And so if I run this, okay, make thread lambda atomic, okay, I'm going to always get 1. Always. Okay, because this is an atomic int. So the C++ threading library is handling this behavior for us. Is this a good approach? Anyone see any problems with this? Is this a good approach? We solve the problem. We can all go home, we're happy, our number I is always printing out 1. Is this a good way of doing it?
Well, if I is doing the right thing, doesn't mean other things are, right?
Okay, well, if I is doing the right thing, doesn't mean other things are, yeah, sure, okay, but in this context, is this the right approach? Have we solved our problem?
Is it fast?
Is it fast? What do you mean?
Is it fast?
Is it fast? Okay, so let's talk about performance, okay? 10 points for you for getting the right answer. Performance. The purpose of multi-threaded code is to improve performance. But atomic operations, okay, whereabouts we have to lock this code, slow down our code because they've got to synchronize. So synchronize is whereabouts everything has to pause and wait until something goes and runs a critical section, okay? And so how you structure multi-threaded code has a very large influence on performance, okay? Hint, hint, this is a very large hint towards how you might approach the assignment, okay? So in this example back here, for atomic operation, every time we need to call I++ and I minus minus, we have to lock that atomic int. So in this case, I am doing this 1,000,000 times. There is 1,000,000 locks on I there, and there's 1,000,000 locks on the decrement there. I'm locking this one singular variable 2,000,000 times. That's awfully slow. That's awfully slow. Let's actually try to run this. Actually, I'll show you something else. Time, Fred, lambda race. Now, I haven't done this in a while, but let's see if it works. Okay, so that took literally 0.006 to run. Funnily enough, that got the right answer. Okay, I run it again. I get the wrong answer, but it took the same amount of time. It was very fast. I run this Fred lambda atomic, okay, 0.58 of a second, okay? It's still fast, okay? There's no question about that. That's still fast. But it's, look at 0.58 wherever it was. That's 58 times slower than my other one. 58 times slower. It's not just parallelized by 2. This is really slow. It's doing so much more, okay? And you think for 0.58 of a second, that's still pretty fast. Try to sort 1 million items on atomic ints and see what your performance is like, okay? So this is a huge problem, okay? So what might we structure, question, yep?
Oh, it might come quick now, I guess. I just wondered, but yeah, okay, I think it's my answer.
Sorry?
Say, but don't we need to lock it anyway?
Well, we're going to get there. We're going to get there, okay? We're not actually going to lock it, okay? So in our example, what we've just seen, we've locked it every time. How might we do this better? Here you go. Simple. Let's use a local variable. Int k is equal to 0, k plus plus. Now, generally, your math in this situation is going to be much more complex than just plus, plus, minus, minus. Then at the end, we just have I plus equals k. Okay? And so we're still with atomic int up here, but we've created a local variable. We only need to read, or actually write to this atomic variable once. So we've just decreased from 2 million writes to 2. 2 million writes down to 2. Now, I'm just going to double check again if I have the solution to this. No, that's not it. Okay, so let me just quickly change this code around to have this value go in. Okay, int k is equal to 0, k plus plus, I plus equals k. I'm sure I've got this example somewhere, but whatever. Okay, let's do the same thing here. Let's do minus equals. Okay, let's hope my code, I just code in 2 seconds works. Okay, make Fred lambda atomic. Time it, 15, 5, 16, 5, 7, 15. So this is still slower than my one with the race condition, but can you see just how much faster that is? Okay, so it has still slowed it down. That's still, in terms of performance, slowed down a little bit. Okay, but that's a huge difference compared to that 2 million locks that were going on. And again, the more complex that math is, the bigger that performance is going to have on your code. Hint, hint, assignment 2, so assignment 4, as you saw, that radix sort, that parallel bucket sort lambda function I gave you was about 10 or 20 lines long. Okay? There's huge performance gains to be made there. Yeah.
The number is now 2 million.
What? The number is now 2,000,001. What have I done?
Say I plus equals k. That's going to be a plus right there. Wait,
Sorry. Yeah.
so this slide.
Oh, yes, I've got the slide wrong. Oh, okay, so that is always 1. Okay? Question? Yep.
If we were to take out the atomic aspect and make I just a regular n,
Yep.
would that solve our problem?
Would that solve a problem if we just made that I just equal to a normal int? Well, now I'm potentially writing to it at the same time. So,
It's only the 2 operations. So
yeah, but I still can have a race condition just on those 2 operations. I can still absolutely at that point have a race condition on those 2 operations. So, no, that int still needs to stay atomic, because that's still a critical section of our code. Okay? But it only needs to be written to once. Okay? Now, there's one final bit of atomic operations, and I've got literally about 20 seconds before the lecture recording cuts off, but there's these things called fetch add, for instance, and this might be an example whereabouts you're trying to get a value and also increment it as you go. So fetch add 5, what it does, is it gets the initial value, it fetches the current one and increases it by 5.